Continuing on section 3.2, coefficient of variation. A disadvantage of the standard deviation as a comparative measure of variation is that it depends on the units of measurement. This means that it is difficult to use the standard deviation to compare measurements from different populations. So, for example, if somebody has worked out, say, heights of people, somebody has measured them in feet, somebody else has measured them in inches, then the standard deviation will change. So it is for this reason statisticians have defined what is called coefficient of variation. Coefficient of variation, which expresses the standard deviation as a percentage of the sample or population mean. So you are looking at percentage of the sample or population mean. What does that mean? Let's look at this. So, coefficient of variation. For a sample, X bar denotes sample mean, S denotes sample standard deviation. Then the sample coefficient of variation, CV, is S over X bar times 100. So that's what gives you the percent part. And this is simply coefficient as in the sense of a ratio. S over mean, standard deviation over mean, times 100 percentage. Now instead of sample, suppose you are looking at a population, then mu and sigma represent population mean and population standard deviation. Then the population coefficient of variation, CV, is standard deviation over the mean times 100. Notice that the numerator and denominator in the definition of coefficient of variation have the same units. So CV has no units of measurement. It's simply a percent. Okay. Now, this gives us the advantage of being able to directly compare the variability of two different populations using the coefficient of variation. In the next example, we will compute the coefficient of variation of a population and of a sample and then compare the results. So, you have Trading Post on Grand Mesa is a small family-run store in a remote part of Colorado. Grand Mesa region contains many good fishing lakes. So the Trading Post sells spinners. What is a spinner? It's a type of fishing lure. The store has a very limited selection of spinners. In fact, the Trading Post has only 8 different types of spinners. The price in dollars are, there are 8 different types. So 1, 2, 3, 4, 5, 6, 7, 8. Since the Trading Post has only 8 different kinds of spinners for sale, we consider the 8 data values to be population. So we are simply looking at the population. Using calculator and appropriate statistics keys to verify, well, you can calculate, find the mean and standard deviation. All right. Now, since the computation for formulas for X bar and mu are identical, most calculators provide the value of X bar only. Okay. Use the output key of this key for mu. All right. So basically they are talking, if in case you are using calculator, X bar typically means mu. Okay. In a population. X bar actually stands for sample, but most computation formulas involve X bar. So they only, calculators only offer X bar. So find for X bar. But standard deviation for a sample is different from that of a population. So make sure you're using the population sigma. Sometimes sigma is denoted by sigma sub n or sigma sub x. Now you have found mean and standard deviation. Now, standard deviation over mean times 100. you should get coefficient of variation to be 10.28%. Interpretation. The coefficient of variation can be thought of as a measure of the spread of data relative to the average of the data. Since the trading post is very small, it carries a small selection of spinners that are priced similarly. The CV tells us that the standard deviation of the spinner prices is only 10.28% of the mean. So standard deviation is only 10.28% of the mean. That's what you were able to say with this calculation. All right. Next, Chebyshev's theorem. Chebyshev's theorem states the following. Okay, before that, let's understand. Concept of data spread above the mean can be expressed quite generally for all data distributions, be it skewed, symmetric, or other types, by using the remarkable Chebyshev's theorem. Chebyshev's theorem says for any set of data, either population or sample, and for any constant k greater than 1, the proportion of the data that must lie within k standard deviations on either side of the mean is at least 1 minus 1 over k squared. So what this says is for any, even if you are skewed, right? You know the mean. Suppose you are given any constant k greater than 1. The proportion of data that must lie within a k standard deviations on either side of the mean is at least 1 minus 1 over k squared. So note important points. Constant k has to be greater than 1 within k standard deviations. And here is at least. The proportion of the data that lie is at least 1 minus 1 over k squared. For example, within 2 standard deviations, you get at least 75%. Within 3 standard deviations of the mean, you get at least 88.9%. Within 4 standard deviations, you get at least 93.8%. Okay? How did we get that 5% here, right? 2 standard deviations. So k is 2. If k is 2, remember the Chebyshev's 1 minus 1 over k squared. K is 2. So 1 minus 1 over 2 squared. 1 minus 1 over 4. It is 3/4. What is 3/4? It is 75 cents or 75%. That's the minimum percentage. All right. Note that Chebyshev's theorem refers to the minimum percentage of data that must fall within this specified number of standard deviations. If the distribution is mound-shaped, an even greater percentage of data will fall into the specified intervals. All right, that's important. In fact, you will see later when you see normal curves, more percentage falls, okay? Because normal curves are mound-shaped and even, fairly even, left-right symmetric. Whereas Chebyshev's handles any kind of data, so even skewed ones, okay? Next, Students Who Care is a student volunteer program in which college students donate work time to various community projects such as planting trees. Professor Gill is the faculty sponsor for this student volunteer program. For several years, Dr. Gill has kept a careful record of X, that is total number of work hours volunteered by a student in the program. For a random sample of students in the program, the mean is 29.1 hours each semester. Standard deviation of 1.7 hours each semester. Okay. Find an interval A to B for the number of students volunteered into which at least 75% of the students would fit. Well, you know the mean and you know the standard deviation. So let's use Chebyshev's result. Chebyshev's theorem says at least 75% must fall within two standard deviations. Mean is this, standard deviation is this. So you're looking from mean minus 2s, mean plus 2s. Look, these should be bars, but the bars don't stay in the same place, it seems, okay? So if you like, whoa, I'm not able to move it. Anyhow, I hope it's clear. X should come with a bar of its own. So you're looking at two standard deviations, 2s and 2s. Subtract, add. So 29 minus 2 times 1.7 to 29 plus 2 points. So using the calculator, you can find these values. At least 75% of the students would fit in the group that volunteered from 25.7 to 32.5 hours each semester. All right. So this completes section 3.2. Next videos will cover problems on section 3.2. Until then, bye.